Okay, now that we're done with the concept of the Coulomb's law, let's talk about the another concept, the concept of electric field intensity. So, if we have here a charge, let's take a constant fixed charge Q in a fixed position. Then around this one, I move another charge. I call it this one. I just call it small letter Q. And this small letter Q, this charge here, this is called the test charge. So what does this mean? This means if I put that charge there, around the charge, it will experience a force around it. If I move that charge anywhere around that positive capital letter Q charge, and this test charge is, actually does not exist. This is just a test charge. It's a test charge. So if I have a charge Q, now there will be a force experience here if this is positive Q. F, force F at that point. And if we solve that, we already using Coulomb's law. That force F is equal to Q times Q all over 4 pi epsilon naught epsilon R. Then if the distance here from here to this one, let's just call it R squared, then you multiply it with that direction of that vector R, if that is the vector R. This is the formula. Now, because small q here does not exist, it's a test charge. So there's a field around this positive q charge, and that is a force field. Now, if we convert that one, we actually call that one electric field. That quantity, that when I put a charge of 1 coulomb, I will have that force that will be experienced to that charge. That's the definition of, a basic definition of electric field intensity. So a electric field intensity, that's the force experienced by a unit of charge or coulomb. So if we divide that force with that test charge Q, so this will be equal to Q all over 4 pi epsilon naught epsilon R times R squared AR. And this expression at the right side, this is what we call the electric field intensity. And we will call this one E. And if you look at the unit for force is Newton, unit for Q is Coulomb, so this will be in Newton per Coulomb. So this is our electric field intensity. If you want to determine the electric field intensity at every point around a charge, so you will use this formula, and that value depends on the distance from the charge and also the medium around that one. Now, there is another unit for this electric field intensity. Mostly we don't use Newton per Coulomb in electrical engineering. You remember from circuits 1, the electron theory. If you try to move an electron inside a conductor, that movement is called the current, and the cause of movement is called the voltage, or the potential difference, or the electromotive force, or simply voltage. And that voltage is determined by how much energy needed to move those electrons. And those electrons are measured not in electrons but in charge. So the unit for voltage is volt, 1 volt. And the unit for energy we use is joules, and the unit for charge is coulomb. So therefore, another unit for voltage is 1 joule per coulomb. 1 volt is equivalent to 1 joule per coulomb. So this is from circuits 1. Now, as we know from physics and mechanics, 1 joule is equivalent to 1 Newton meter. So therefore, 1 volt is equivalent to 1. I changed that joules to Newton meter, so Newton meter per coulomb. And look at this. This is that Newton per coulomb here. So if I cross multiply, I put meter at the other side, 1 volt per meter now will be equivalent to 1 Newton per coulomb. So this means another unit for electric field intensity. We actually used volt per meter. So the unit for electric field intensity is volt per meter. We use this one instead of Newton per coulomb. Now, from this, we can derive another concept because this is volt per meter. So if we try to multiply the distance to that electric field intensity, so we multiply it with meter, and we will get volt, the unit volt. And that voltage, we call it the electrostatic potential. Electrostatic potential. Potential. So this is the electric potential resulting from the location of the charge from the bodies in around that charge, and we call it V. So if we solve for this, the value for this one V will be equal to the electric field intensity. Then you multiply it with the distance r, where this is simply equal to electric field intensity is this one. I just multiply this one with r, then I will be having q all over 4 pi epsilon naught epsilon r. So the other r will cancel out. This will be just IR. So mostly for a voltage, we only need to know the magnitude. So if I remove the direction of that one, then this will be our value for the magnitude of the electrostatic potential. And the unit here will be in volts. Volt. 1 volt. So that's electrostatic potential. Now let's take an example. So this is the example. Find the electric field intensity at the origin due to a point charge of 64.4 nanocoulomb located at -4, 3, 2 in Cartesian coordinates. So this is a very straightforward problem. We just need to solve for the electric field intensity at the origin. If we have a charge around the origin that is located at -4, 3, and 2. Let's try to plot that. -4, 3, and 2. So this is the graph. So at this point, this would be where the charge is equal to 64.4 nanocoulomb, and we want to determine the electric field here at the origin. So let's try to take this one. So if here you have the charge at this point, and the charge here is 64.4 nanocoulomb, and we want to determine the electric field at this point, so the direction will be in that direction. this vector here, this one will be our r, vector r. So this point, remember, is this is n negative 4, 3, and 2. That's the location of the charge q. So to solve for E in this graph, we need to determine R. So remember, E is equal to Q all over 4 pi. So this will be in free space. So let's just multiply this one with epsilon naught times the distance, or the magnitude of that vector R, multiplied with the direction of that vector R. So we have a charge 64.94. So we only need to determine AR and R. So how do we determine R? R will be equal to what? So this is in the origin. It's going to the origin. So the position vectors, we just subtract them. What are the position vector? Negative 4, 3, 2. And the other one, 0, 0, 0. So the origin is the end point, and this is the starting point. So we subtract. So 0 minus negative 4. So this is plus 4 EX. Then 0 minus 3, so minus 3 AY. Then 0 minus 2 minus 2 AZ. And that will be our vector, displacement vector, or directed vector. And to solve for the electric field now, this will be equal to Q, which is 64.4 times 10 to the negative 9. It's nano. All over 4 pi epsilon. 4 pi epsilon, this is constant. Then you multiply it with the magnitude of R, and that is the square root of this, and you square that, or this is simply equal to 4 squared plus 3 squared plus 2 squared. Then you need to square this one. I forgot, you need to square this one. You square root, then you square that. So I just cancel out the square and the square root. So it's just 4 squared plus 3 squared plus 2 squared. And this is around 4 squared plus 3 squared plus 2 squared. That's equal to 29. Then AR, you multiply this one with the unit vector. What's the unit vector? AR. So the unit vector is the vector itself divided by its magnitude. So this will be 4AX minus 3AY minus 2AZ. That's the vector R. And you divide it with its magnitude, which is equal to 4 squared plus 3 squared plus 2 squared. And you take the square root, and that will be square root of 29. Okay? And this will be our electric field. So we simplify this one. This one will be equal to 64.4 raised to negative 9. Divided with 4 shift by shift constant 32 times 29. This will be equal to 19.958, or that is around 20. You can round that off to 20. Then you multiply it with that one, 4 over square root of 29. 4AX minus 3AY minus 2AZ all over square root of 29. I don't need to distribute that one. It's better. It's better if it's in this format. Why? Because the magnitude will be obviously 20, and the unit vector is this one. So this means this is the direction, and this is the magnitude, and the unit for this will be volt per meter. So the electric field intensity at point or the origin is equal to the magnitude is 20 volt per meter, and there's the direction. Let's take another example. So this is another example. Find the electric field at 005 due to Q1 0.35 microcoulomb at 040 and Q2 equals negative 0.55 microcoulomb at 300. So let's try again to plot this one. Here. So this will be the graph. So this is 005. So this is where we want to determine the electric field S. And these are the two charges. So let's try to snip this one. And paste it. So this is now our graph. So this is 300 at this point. 300. And this is Q1. And it's equal to 0.35 microcoulomb. So this is 300. And while this one is another charge, 040. And this is Q2. And it's negative. Don't worry about the negative. Later on, is it true that it's in that direction? I don't think so, but because of that negative here, I will put that negative. It will correct the direction later on in our calculation. So don't worry about that. So at this point, 050, so we need to determine the electric field at this point. So what are the effects? So to solve for the electric field, we need, just like the force before, we can apply superposition theorem. We need to determine the effects of each charge. Then after that, we just need to add them. So I can call this one due to Q2, F2. I call this one due to Q1, F1. So that's F2, this is R2, and this is R1, position vectors. Or instead of force, it's electric field E1, E2. So the net now will be just the sum of the two. So the total now, E, at that point, E will be equal to E1 plus E2. So just like what we did before in Coulomb's law, the forces, it's the same. We just remove the other Q. So we need to determine E1 and E2. So determine E1 and E2. First, we need to know R1, our directed distance or displacement vectors. So R1, remember this is 300 and this point is 005. So you just subtract them. So R1 will be equal to 0 minus 3. That's negative 3 AX. Then 0 minus 0. So there's no Y component. Then 5 minus 0 is positive 5. So add plus 5 AZ. Then for R2 will be equal to, again, 0 minus 0, there's no EX, 0 minus 4, negative 4, that's in AY. and 5 minus 0 is positive 5 in z direction. So these are R1 and R2. Now we know R1 and we know R2. We can now solve for E1 and E2. So E1 now will be equal to the formula. You can just directly solve E. So the total E will be equal to E1. What is E1? It's Q1 over 4 pi epsilon naught times R1 squared AR1. Then we add the other one, Q2 all over 4 pi epsilon naught R2 squared AR2. So AR1 is equal to R1 over the magnitude. AR2 is equal to R2 over the magnitude. And this will be equal to so what's Q1? Q1 is 0.35 micro. So 0.35 times 10 to the negative 6 all over 4 pi epsilon naught. Then what will be R1? The magnitude. So you just remove the square root. You just square the components of R1. R1 is negative 3ax plus 5az. So this will be 3 squared plus 5 squared. And you multiply it with the vector, unit vector. So the vector itself, negative 3ax plus 5az all over the magnitude, which is the square root of 3 squared plus 5 squared. 3 squared, 9 plus 9 plus 25. And that is equal to 34 squared of 34. So this will be 34. And that will be the unit vector. Then you add the other one plus Q2. Q2 is negative 0.55 times 10 to the negative 6. Include the negative all over 4 pi epsilon naught. You multiply it with 4 squared plus 5 squared. 4 squared plus 5 squared, 25 plus 16, and that's 21. Then you multiply the unit vector AR2, negative 4ay plus 5az divided with the magnitude square root of 41. 16 plus 25. Okay, then simplify this. You can now solve this one. And this will result to AZ and AX. So we all have AX, AY, and AZ components. Let's just solve this. This will be 0.35 all over 4 shift by shift constant 32 times 3 squared plus 5 squared, and that's 34. 34 equals. That will be equal to 92. 92.52. This will be 92.52. You multiply it with negative. I can still divide this one with square root of 34. We can distribute that because we need to add that in the other one. So let's just multiply it with 1 over, or we just make this one raised to 3 halves or square. Or cube. Should be cube. Three. and that is around 15.87. So this will be 15.87 multiplied with negative 3ax plus 5az. Then the other one, negative 0.55 exponent negative 6 all over 4 shaped by shape constant 32. Then you multiply it with the square root of 41, and we just need to cube this one. Cube. And this will be equal to minus 18.83. Then you multiply it with negative 4 ay plus 5 az. Then we combine all the ax and we combine all the ay and az. So 15 times negative 3, 15.87 times 3. That will be... I made a error here. Q1 should be located at 040, but in our drawing, Q1 was in 300, and Q2 should be located in 04 Q2 at 300. So they're interchanged, but we already did the solution here. So what we do here is to interchange the value of Q1 and Q2. But instead of doing that, let's just change the problem. Just make this one 300, 300, and this one is at 040. Sorry for that. So that the drawing is still correct and our solution still be valid. So here now we have a negative value for ax. It should be negative 15.87 times 3, and that is 47.61. So this is negative 47.61 ax. Then we have negative 18.83 times 4. Negative will be positive. So 18.83 times 4. That is 75.32. So plus 75.32 in the y direction. And for the z direction, so we need to add 15 times 15.87 times 5. Then we need to subtract it with 18.83 times 5. 0.83 times 5. And that is 14.8. It's a negative. This should be negative. So minus 14.8 ay, and this will be our electric field at that point. And the unit will be in volt per meter. Volt per meter. If you need to determine the magnitude now of E, it will be just equal to the square root of 47.61 squared plus 75.32 squared plus 14.8 squared. So that will be the magnitude of E. So that is electrical intensity. So for the next topic that we'll be discussing what happens if the charge is not a point charge, just like what we we are doing here in our examples. What happens if it's a volume of charge, which is actually in the real world we are dealing with, for example, the conductors, the wires, and the cylinder. Inside that cylinder, there are charges, or the capacitor. The application of electrostatic, the capacitor. Capacitor is composed of plates separated with each other with the dielectric. So that one is not a point charge. It's not just point. The charge is distributed into the plate. So how do we deal with that problems? So in the next discussion, we will be doing that, and we call that one the charge distributions. And we also discuss the different standard charge distribution that we will be using. Okay.